Hey everybody, Lars here. It is Sunday, November 6th, in the middle of NFL football Sunday. Giants won, Cowboys won, Lions beat the Vikings, Jets managed to lose because they scored a touchdown, and then on the very next play, well, actually there was a penalty, and then the Dolphins ran back a kickoff, so the Dolphins beat the Jets. Terrible job. Anyway, as you know, this weekend we're video crazy. So Friday, review video 1. Saturday, class number 3. Sunday, of course, we're going to do review video number 2. The reason I do it, and I think I said it before, is that for whatever reason, we flip-flop assignments. On your assignment number 1 refers to the second half of the slides, the recursion part. And assignment number 2 is the bigger one where we take some numbers and we do some searching and some sorting and some stuff along those lines. So I always want to get you the video, this video that you're going to see right now, before you get the homework assignments. So I'm going to give you the homework. I'll do announcements at the end, but I'm going to give you the homework assignments tomorrow. Today I'm giving you final project stuff, and you'll see we'll all do some announcements later on tonight. But for now, I want to do the second half of the slides, and we're not really going to look at the slides. We're going to do some coding. And I want to introduce you to recursion. Recursion is considered this big boogeyman, and when people hear it, they get scared and blah, blah, blah. It's not that hard. Don't be concerned, because it just needs to be explained properly, and hopefully I am able to explain it properly for you. What I usually tell people when they first, there we go, we're looking at scores. When you first want to get involved with recursion and look at recursion, go read the Wikipedia page, because as you'll see, recursion just doesn't have to do with computer science. Language is generated recursively. It has a lot to do with language and natural language processing and theory as far as that's concerned. It has a lot to do with art, if you know who Escher was, and the Drost effect. As you can see, the woman is holding the cereal tray, and she's got a box just like this box where she's holding a cereal tray, and that has a box where we're holding a cereal tray. It's like going down with the mirror, snakes that eat themselves. Sourdough that needs a little bit of the sourdough that came from the batch before you can start the new batch. Russian dolls. I'm sure there's Russian dolls down here. Gotta be, yes, Russian dolls. There's a whole bunch of different ways. Sierpinski's triangle to understand recursion. And basically, all recursion at the end of the day is something that refers to itself in its definition, which is kind of counterintuitive, because how can I understand something if first I have to understand something? But it's the nature of it that takes you on a journey where you're basically taking a big problem and doing the same thing a whole bunch of times until it becomes a small problem, and then you're coming up the line and adding together all those solutions. And you're going to see as we do one real quick, because actually I'm just going to code one up real quick. Hold the phone. I knew I had some blank. I'm going to call it some recursion. And what I'm going to do is basically I'm going to write real quick a function that, what do I want my function to do? If I go to numbers, say 6, I want to add all the numbers from 0 to 6. So 6, 5, 4, 3, 2, 1 on down that line, okay? So I will say if n, and I will explain it afterwards, so you don't have to explain it now. Return 1, else return n plus my sum n minus 1. Correct. And that's it. And then we're going to use it. I'm going to say a equals my sum. I'm going to say something simple like 5 so we can add it up. And I'll say print a. So when I run this, what's going to happen? Okay, it's going to take 5, and it's going to add 5 plus 4, which is 9, plus 3 is 12, plus 2 is 14, plus 1 is 15. And if the recursion gods are with it, invalid syntax, oh no. Reach run, you think? And if the recursion gods are with us, it will say 15. So let's trace through this code. Actually, you know what we're going to do? We're going to do a simpler. We're going to make it 3, and then we're going to trace it through 6. That's correct. We'll trace it through with C. Okay, so let's trace it. Comments, don't do anything. Defined function, don't do anything. Put it in memory, but don't do anything. Comment, main, don't do anything. First time we do something is here. I'm going to create a variable called A. I'm going to assign it the value I get when I call the function, my sum, with a 3. So I come up here. My sum, n is equal to 3. If n is equal to 1, is it? No. So return n, which is what? 3 plus, and then I call the function again. Only I don't call it with 3, I call it with 2. So I reduce it by 1 and call it again. Now, this is where I think a lot of people get into trouble with recursion. As you're tracing your code, you now see the function name again, because like we said, it's recursive. It's used in its own definition. People will jump up here again and get their minds convoluted because this already has a variable assigned to it, and I thought this was 3, and boom, boom, boom. And then people get confused and kind of go down that rabbit hole. Don't think about using the same code. And as you're going to see in a second when we do multiplication, I set it up this way. Think about it as going and getting another copy of this. This is just a blank function. We go grab another copy of it, and we say my sum of 2. So when I come in here with my new copy, is 2 equal to 1? No. So else return 2 plus my sum of 1. Brand new copy. So when I get my new copy, my sum of 1 is n equal to 1? Yes, it is. So I return 1 to the previous function call. So now this line is going to say return 2 plus 1. So I return 3. Where? To the previous function call. And what is that previous function call? That was the very first time we ran this function. And this is a 3, and this is a 3, so I return a 6. Where do I return the 6 to? The original call. Okay? And then a equals 6, print a, and we get 6 down there. So that's what's happening. Basically, what we're doing is we're noticing that we have an operation where we can take 1 off the list, and then we just want to perform that same operation on the smaller list. So I have 3 numbers, and I want to add them up. Well, let me grab the 1, and then go do this with just 2 numbers. And then that takes it and says, all right, I just want to do a smaller operation. Let me grab 1 number. Go do this with 1 number. And then when you see 1 number, it's a special condition. So we say, all right, go back to the function and go back up the stack. And when we go up the stack, this is your key right here, that plus sign. As we go back up the stack, that operation is going to be implemented every time we go back up. Okay? So you're going to get 1 plus 2, then plus 3, 6, boom. Now this sums numbers. I mean, if I went, 7 and I ran it, yes, I know, then we would, hello, oh, 72, geez Louise. If we just did 7 and ran it, we'd get 28, okay? But just this simply shows you how important it is. Boom. And what did that do? Think about it. Now this is factorial, okay? It's not a sum anymore. I'm going to rename it. Now all of a sudden this is factorial. And if you have a computer science background, you know that factorial is what a lot of computer science professors and teachers use to introduce recursion to students, because it lends itself well to it. I mean, you've got, what is factorial? Is 5 times 4 times 3 times 2 times 1, just like we did with the my sum, 5 plus 4 plus 3. Anytime you have a repeated operation where you want to take 1 off the list and then send the smaller list to the same operation, if you can recognize that as a problem-solving technique, that's where we can use recursion to go at it. So now, just by simply changing that one little sign, all of a sudden now I've taken my recursive function and I've changed it from sum to factorial. So now I can do factorials. Okay, factorial lends itself to recursion. But that kind of creates a problem. At least it was always a problem in my mind. When I first started taking programming classes in the 80s when I was a kid, whatever was used to introduce recursion to computer programming students, be it the Fibonacci sequence or be it factorial, it was always the first time I had seen that. I had never used iteration to tackle Fibonacci. I had never used iteration to tackle factorial, although you can, theoretically. Iteration and recursion are exactly the same. We're not going to get into that, but it's the truth. They are exactly the same process at the end of the day, at least tail recursion, but that's getting into the weeds. So my whole thought when I was a kid was, why aren't they showing us a recursive definition of something we know already? Because then you'll see how it's different, and then you'll see, a new way of looking at doing something you're already familiar with. When it was done with Fibonacci and factorial, that was the first time I ever saw those things done. So it wasn't necessarily special to me, okay? So what I always like to do when I teach computer science, and I will save some recur and I will stick it up in the thing for you, and didn't want to do that, wanted to do this, is I do multiplication. Because since third grade, you've known multiplication. And at the end of the day, what is multiplication? It's a series of additions. That's all multiplication is. You know this. All multiplication is a series of additions. So we can tackle multiplication recursively. Okay? And the way we do it is we just take the number, and then we take the other number, and we reduce that number and set up a series of additions. That's all. The code that you're looking at right there does it. We're going to trace through this code. Well, first I'm going to run it, make sure it works. 9. What am I doing? Yes, it does work. Well, let's make sure. Am I getting 12 when I do that? All right, I think I might be onto something here. I think I might be onto something with this programming. So we're going to trace through this code, but I am going to trace through it in another kind of way, because I promised you I was going to teach you the right way to think about recursion. So I am going to trace through this code, but I'm going to trace through it this way by doing a little bit of drawing. So when I first run my program, I have A equals my mult of 3 and 3. So when I call that program, what do? I come up here, num, we got to make sure we draw this properly. Num is 3 and times is 3. If times is equal to 1, is it? No, it's equal to 3. So I don't return num. Else, return num. What is num? 3. Plus my mult, num, which is still 3. Times minus 1. What's times? 3. So times minus 1 is 2. Okay, now, recursion. This thing right here, what is it doing? We're just calling a fresh new copy. Look at that right there. Boom. A whole new copy of it. That has nothing to do with the old copy we ran. That's still in memory. Only now I'm doing it with num 3 and times 2. Because that's what I called. So, is times equal to 1? No. Else, return num, which is 3. Oh, that was a creepy 3. My mult, num, which is 3, times minus 1. Times is 2, so times minus 1 is 1. Okay? This call right here, where am I going? Dun, da, da, right down here to my fresh new copy of my recursive function. Now, this is exactly how it's being implemented on your computer. This is what interpreters and compilers do with recursive functions. It has nothing to do with something working inside of itself. That's just the definition. It goes and grabs a brand new copy every time it sees it. That's why you're allowed to do recursion. Because when it sees this, it grabs a brand new copy of it. Just because this resides inside makes no difference. You're going to go get a fresh copy every time. So this time I'm getting 3. And I'm getting 1. Is times equal to 1? Dun, 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 dun. Check. Yes, it is. So I return num. What is num? 3. Where do I return it? I return it to the call up here. To this function. So what do I return? I return a 3. So this is a 3. Hello, 3. So now I'm ready to do this return. Num 3 plus 3 is what? 6. Where do I return this 6? To the call, to the original call from the first time I ran the function. Okay? So now this is a 6. Oh, that's a creepy, wow. Wow, how much alone? Oh, good, it only undid that little 6. So this is a 6. So now I'm ready for the last return. Return num plus 6. What's that? Dun, 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 dun. 9. And what is 9? 9's the answer. Okay? I did the 12 down there because I did it to test it. But now that I'm back with 3, 3, and I rerun it, 9. Didn't want to do that. Dun, 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 dun. Okay, let's just get rid of this. Goodness gracious. So that's the way we did it. Looks a little convoluted now, but you know, because you follow the process along the way. We made the list smaller, got down to just one instance, and then came up the stack, adding as we did. until we finally came to our solution here. And as you could probably guess, if I did 3 times 100, we would just go down this stack 100 times. And the same thing would happen. We would add 3 to our number every time. Because what have we gone? We've gone 3 deep in a function stack. And because we went 3 deep, that's how many times we add 3. Num never changes. Take a 3, add it, 6, 9, boom, we're done. That's how far it is, okay? That's how recursion works in this simple example. And that's how a lot of the ways that you will utilize recursion when you begin computer programming, that's the way it'll work. You will recognize problems that are well suited for just taking a little piece off and then taking the smaller subset and throwing that into the same process. So you get down to one thing, and then you come up the stack and you do your operation as you come back up the stack, okay? Watch this a couple times. You'll get the feeling for it. I know it's a little weird. This is another thing. I know a lot of you are saying to yourselves, hey, I've been doing multiplication since the 3rd grade. It's working out for me. Think I got that whole multiplication problem licked. What the hell do I need recursion for? Who cares? What you're going to find out a little bit later down the road is you're going to deal with some data structures in computer science, specifically one called a binary tree, where recursive functions and methods really lend themselves well to creating efficient code that works on these data structures. When you see binary trees, you're going to see their little nodes of trees. And what a binary tree is just a collection of more binary trees. Every node is like its own little binary tree. And if you have a whole bunch of them, then you could write a recursive definition that just says keep going left until I have no more left, then come up, go right, come up, go right, come up, go right. And it's a super efficient way of searching a binary tree, going through a binary tree. You'll see you can use recursive things to sort binary trees, use recursion for sorting. When you see some of those definitions and you see some of those techniques when you get to binary trees, you're gonna do a double take and you go, okay, now I get recursion. Now I kind of get it. It's a simple way of saying, hey, keep doing this, keep doing this, keep doing this. Okay, we've reached our final condition. Now let's come back up the stack and do things up the stack and add things and sort things and search things. You'll see, you'll get it. So don't think this isn't just us, fooling around for the sake of fooling around. Recursion comes into play pretty big programming wise later on down the road, as far as binary trees and some other things that you'll see. And you can always, if you read that Wikipedia page, you'll learn about Sierpinski's triangle and how you can do some drawing and stuff like that, and you can look at Mandelbrot and other things like that. And you'll see what I'm not gonna bust you over the head with this. The stuff that I'm giving you a programming assignment on it, but it's not hard. It's not hard. You watch this video, you're gonna be able to do that assignment in literally 10 minutes. Okay. I'd want you, like I always say, I want you to be exposed to this stuff. I want you to be familiar with the terms. I want you to have seen it and considered it and thought about it. So later on down the line in your data science careers, when you do run into it, then you're going to be like, oh, yeah, I remember that Python class. And yeah, I remember recursion and I did A, B, and C. And I know about factorial and I know about Fibonacci. But I saw it done with multiplication. So I know how it's done the classic way and the recursive way, blah, blah, blah. All right? All right, good. Then I am going to do some announcements, which hopefully are going to be pretty easy because as of now, no, that's a lie. As of tomorrow, you will have all your resources for Unit 4. I got you the first review video. This is the second review video. I got you Class 3 last night. Today, I put together the resources necessary to get you all the information you need for the final project. You're set up with your groups. You're set up with your group forums. You now have the info sheet for your final project, and I put up some examples in the Sakai resources. Your first deliverable, your proposal, make sure you get it to me November 16th. I know that's only 10 days from now, but I really need to see them because I need to see them and approve them so that you can get to work, and then the design document's not due till December. So you have a lot of time to work on that. But I do want you to put together a proposal and a decent idea because I might not just come back to you and say approved right away. I might come back to you and say, well, what if you tried it with this kind of data? Or what if you did this kind of thing? Or what if you did that kind of thing? That's all. So don't worry about that, all right? So and I'll do an announcement later tonight. So you've got your final project stuff now. That's done. Tomorrow, I will release the 2 assignments, maybe even at midnight tonight if I cheat a little bit. so that you'll have the 2 assignments for Unit 4 that are going to be due at the end of the week because we extended the time a little bit to a week from today. November 13th is going to be the last day for Unit 4. All right. Good job with all your midterm projects, although I'll be honest with you, I haven't even looked yet. So make sure you get in all those midterm projects. Don't get that in late because when I start grading them, I better see them all there. So we're chugging along. We're doing good. Part of my life's mission this week coming up is going to be to do your grades for Unit 3. So hopefully that'll be along the line soon. Don't worry about that right now. Worry about Unit 4 stuff. All right. Once you get your assignments, you'll have all your stuff for Unit 4, and you should be good to go with that. Okay. All right. Then we're in pretty good shape. You keep chugging along. Just keep Unit 4 on your brain until the end of the week, and then the 13th is going to be the quiz. That's when the 2 assignments are going to be due. That's when the forum post is going to be due. Read the short story, Logic Named Joe. Comment on it. Let me know what you think. And start talking with your group mates and start thinking proposal. Doesn't have to be 5 million pages long. 3 pages long. Make it like a Shark Tank pitch. I'm not interested in knowing about data and code and blah, blah, blah. Make a pitch. Pitch what you want to do. Okay? Make it like you're throwing out an idea. Make it like an elevator speech. Doesn't have to be super long. 2-3 pages. Read some of the examples. The examples are good. Okay? All right. Then I'm getting out of here. You have a good rest of the day today, and you have a good week, and I'll be in touch in a couple of days, and everything is going to be good. All right? All right. You be good. I'll talk to you later. Bye.